Good morning. This is our second lecture on SVM. In previous lecture, we have seen that the basic terminologies which will be useful in SVM, and in this lecture, we are going to see how SVM is forming a boundary for linearly separable data. As you know, the perceptron is also used for forming the hyperplane for linearly separable data. But due to some limitations of perceptron, we need SVM. So what are that limitations? First is, even if linearly separable data is available with us, sometimes perceptron will converge, or sometimes it will not guarantee. Basically, it will not guarantee that it will always converge, because that convergence is depend upon the initial value what we take. That initial value depends upon the convergence is matter. Second disadvantage is that it takes a long time. It takes a here you can say that it takes long time, especially when gap between classes is very small. uh, Suppose the hyperplane margin is very small, means this class data or this class data, they are not well separated, then it will be a limitation of perceptron. It will not converge fastly. So uh, question is that, can we increase the gap between classes? Yes, by doing the transformation. What is meant by transformation? transformation Transformation is, suppose we have data in x space, and we can solve that in higher space, that is x square or 3x space, anything. Okay. Third disadvantage is that, and this is the main disadvantage, that if data is linearly separable, sorry, if data is not linearly separable, then it loops, means it will not converge. Example is that XOR problem. It will perceptron will not solve the XOR problem, and that is the basic problem. Means we can say that ki, perceptron is not working for simple problem, then why we can use. So due to these reasons, we move to support vector machines. We already seen that the perceptron not particular solution, so it will, because it will not always guarantee, that's why we go to SVM. SVM gives us a optimal solution. So we are actually finding the optimal solution for linearly separable data. Optimal solution or optimal hyperplane. So optimal separating hyperplane means what? This hyperplane is the center of the separating region. This hyperplane is the center of separating region, or it maximizes the distance between the closest point. This is the closest point, this is the closest point, this is the closest point. It will maximize, this width is maximize the between the hyperplane. Okay. Closest point from both classes should be at same distance from the hyperplane. This distance from this class point, this is the closest point, to this hyperplane is same like this. Okay. We have to choose appropriate orientation of hyperplane to that distance should be maximized. So when we need uh, orientation, here we can say that this point is closer to this hyperplane, but this point is close, this point is close to hyperplane. So distance between this and this should be same, but here you can see that the distance between this point to this hyperplane is smaller as compared to this. So we need a orientation, because from both side we need a same distance. So we do orientation, so we will move this boundary to this side, so that the distance between both the same. So we can say that we need a maximum margin hyperplane. So what is margin? This from this that closest point to hyperplane distance is called as margin. Okay, so our objective is that we have to maximize m subject to what? Yi multiplied by xi transpose beta plus beta naught is greater than or equal to m. What is m? Margin. Okay, and what this xi transpose beta plus beta naught? That is the sign distance from hyperplane. Xi varies from I is equal to 1 to n, means these are the our data points. Every data point should be at least a distance m from hyperplane army. Okay, this is the every data point, these are the data points, these are at least m away from this hyperplane, means inside this region no data points will occur. Okay, then why we are multiplying it with y? Because we want a result always pair positive, that's why we are using y. What is the next is question is that what is the distance of closest point? What is the distance of closest point? I think this is the closest point for this class, and this is the closest point for this class. So we can say that whatever m we don't know, so whatever optimal in whatever optimal m will be the distance of the closest point. Okay, so norm of beta is equal to 1, because we do not want solution will blow arbitrarily means it will not blow randomly, you can say that. So for this we have to normalize, that's why we will add 1 upon norm of beta yi, other thing is as it is. So we are normalizing beta because we don't want the solution will blow up. So in next step I can move this beta here. So yi xi transpose beta plus beta naught is greater than. Okay, if something satisfies this constant, actually this is the constant which maximize this m. Okay, satisfy the constants, so I can arbitrarily set mod of beta is equal to 1 by m. This is an assumption taken, this is a normal property, and we can set that arbitrarily. Okay, so if I will use norm of beta is equal to 1 by m, then instead of this I can put 1, then our objective function will now minimize norm of beta subject to yi xi transpose beta plus beta naught greater than or equal to 1, or norm of beta is equal to 1 by m. Okay, and here we are multiplying by 1 by 2 and squaring up. We are just normalizing that because it will be useful to take derivative and other things. So margin is actually going to be, what margin will be? 1 upon norm of beta. 1 upon this margin will be a 1 upon norm of beta. Okay, so what we are doing, we are trying to find out a minimum norm solution such that all the data points are correctly classified, all the data points are correctly classified. Actually along with correctly classified, we are ensuring that we must be certain away from hyperplane. Okay, so this is our objective function. So here we can use Lagrangian multiplier. So Lagrangian multiplier primal form is this is our main we have to maximize, so maximization function minus summation of I is equal to 1 to n, that constant. Okay, so here we have written the primal form. So I may be 1 to n because we will run it for every data point. Okay, p denotes the primal and d denotes the dual. Dual will be the easy to solve. Setting derivative to 0, we are setting derivative is equal to 0. So Suppose the above function, this we will derive it with respect to beta, then we will get beta is equal to, here 0 will be there because we have set a derivative with 0, and this function gives beta minus this will give with respect to, suppose we respect derivative with respect to beta, then we will get alpha I I and xi. Okay, xi transpose can be written as xi. Okay, and this minus, so beta will come this side, so beta will be positive and this will be positive. We can call it as first condition. And this function again we will call differentiate with respect to beta naught. So if you will derivative with beta naught, this function will get 0, and here we will get summation of I is equal to 1 to n alpha I yi. Okay, and other things are 0. This we will call that as second equation. uh, Suppose we will get a dual of Lagrange in Lagrangian, that will come like that. LD is equal to summation I is equal to I is equal to 1 to n alpha I minus 1 by 2 summation of I is equal to 1 to n k is equal to 1 to n and alpha I alpha k yk xi transpose xk based on this condition. Okay, and subject to alpha I is greater than 0 for all I. This we will call it as third equation. This is looks like simpler because we have to consider only alpha I, and that should be a non-negative. Okay, non-negative means positive. Okay, so what we will get, alpha I in multiplication yi xi transpose beta plus beta naught minus 1 is equal to 0 for all I. This is our fourth condition. These conditions all 1 to 4 are called as Kkt conditions, that you can see by Google, by using Google. Just type what are the Kkt condition. These are similar like this. Okay, and that needs to be satisfied. So what does it tells? We know what form of beta should be. It has to be alpha I. Here we can see that it has to be alpha I yi xi. Our beta is taking our out certain data points from our training data and adding them up. Okay, next is fourth condition needs to be satisfied. Fourth condition needs to be satisfied. When LHS of 4 is 0, when where is the fourth condition, LHS of this is 0, then alpha is 0 or bracket is 0, then one must be 0, then only this and will be 0. Okay, when alpha has to be 0, when alpha has to 0, when yi transpose this bracket term is not 0. Okay, alpha has to 0, then this bracket term will not be 0. When xi is closest point, it comes on a margin. Xi is a closest point. अगर closest point है, it will come on margin. Okay, so we can call it as a support vector also. Okay, if we have anything will come in margin, we can call it as m, that m point margin our. Okay, okay, so for this point value is, and this point value, for this point value is 0. Okay, okay, you can say that this point and this point here term is greater than 1. Why? Because they are far away from the margin. Okay, or hyperplane. Bracket term is non-zero, so here bracket term is non-zero, so alpha has to be 0. Because bracket term is non-zero, then this alpha should be 0, so that our fourth condition will satisfy. Okay, what it means? It means that points that are further away from hyperplane do not contribute in finding beta because alphas are 0. Okay, The points which are contributing beta are exactly points which are on that margin. Basically we are doing this 0 where we want this value 0 because we are sorry, we want those points value will be 0 which are contributing in finding the hyperplane. Suppose this value is there, this value this point is there. For this value will be 0 because this is we can consider it as support vector because it is contributing in finding the margin. Okay, so we can say that whatever lies on this margin and this margin are support vectors. Okay, so our um, functions, objective function will be such that yi xi transpose beta plus beta naught is greater than 1, then alpha I is equal to 0. If alpha is greater than 0, then we can say that yi xi transpose beta plus beta naught is equal to 1, that these xi are the support vectors because alpha is not non-zero, that is greater than 0. Beta is going to depend on only support vectors and beta value will be depend on only support vectors. Suppose we have to find out the beta naught, then we can plug in any support vector or any support point in this equation, then we can get beta naught. But basically question is that which support point should we put? So due to some numerical reasons, basically what happens, we will put all the support vectors, whatever may be the support vectors, we will put in this. So first we will put in this equation, then we will find out beta naught, then second we will put in this one, then again find out beta naught. So whatever may be the, suppose there are 5 support vectors, then we will put 5 values, we take sum of them and average it, and according to that we can find out the beta naught. Okay, this is actually in this lecture we have covered how to find out this margin, how to fix this margin. Okay, so we got finally these conditions to find out the support vectors. According to the support vectors we can find out the hyperplane, best suitable hyperplane for linearly separable data. Now the question is that if the data is not linearly separable, means linearly inseparable data is there. So linearly is inseparable data means this star or this star, this data point may lie here, something here, from this data point one of the data point lies here, then how to find out the decision boundary for that or hyperplane, for that we will see in next lecture. Thank you.